The Strait of Gibraltar, known historically as the Fredum Herculeum, or Pillars of Hercules, represents the aquatic passage linking the Atlantic Ocean with the Mediterranean. Measuring just over 8 miles, or approximately 13 kilometers, at its narrowest span, this relatively compact body of water separates two continents. Paradoxically, despite this minimal distance, and the existence of 60-plus globally constructed bridges exceeding 8 miles in length, no infrastructure has yet spanned this intercontinental gap. This absence raises compelling questions about feasibility and engineering capability. The prospect of bridging Europe and Africa has attracted serious consideration for decades. Geopolitical weight would be substantial. It would forge connections between 447 million European Union residents and 1.4 billion African inhabitants. The economic potential remains transformative, enhanced commerce and streamlined transport between these continental regions. Yet, despite decades of feasibility studies and ambitious proposals, the project remains unrealized. The question persists: can a vehicular or rail passage ever traverse the strait? The answer involves far more complexity than distance alone suggests. The Atlantic to Mediterranean waterway spans roughly 36 miles in total length. Where Point Morocco in Spain meets Point Suez in Morocco, the passage constricts to just over 8 miles, comparable to the San Francisco-Oakland expanse. On clear days, you can actually see across to the other side. Submerged depths reach an average of 1,200 feet, or approximately 365 meters. Yet the strait's defining characteristic remains its status as a paramount maritime corridor. It functions as the sole natural passage joining the Mediterranean to an open ocean. The Suez Canal, though connecting Mediterranean region waters to the Indian Ocean via the Red Sea, was engineered artificially. The strait exceeds the Suez in both scale and navigability for larger vessels, rendering it optimal for commercial navigation. This translates to extraordinary maritime traffic. Approximately 100,000 annual vessel transits occur, substantially surpassing the Panama Canals' roughly 14,000 annual passages, or the Suez, approximately 20,000. Vessels constantly circulate petroleum, minerals, and manufacturers toward Asia, the Middle East, and Western markets. The petroleum component proves especially substantial. Daily oil carrier passages exceed 300 vessels. A compact tanker transports between 70,000 and 190,000 barrels, roughly 3.2 to 8 million gallons. Larger variants hold between 190,000 and 345,000 barrels, around 8 to 14.5 million gallons. On high-traffic days, nearly 2.4 billion gallons of crude transit the channel, almost triple the United States' daily petroleum consumption of approximately 840 million gallons. This economic reality has spurred port expansion throughout the region. Spain's port of Algeciras ranks among Europe's preeminent facilities and the Mediterranean's largest, while Morocco's port of Tangier Med experiences rapid growth as a continental trading nexus. Given such lucrative commerce, one naturally anticipates infrastructure development. Yet the intercontinental link remains absent. Why? Feasibility analyses undertaken repeatedly since 1979 have identified surmountable engineering challenges alongside formidable obstacles. Contemporary engineering capacity renders such a bridge theoretically constructible. Numerous structures spanning comparable distances function regularly. The genuine complication concerns preserving unrestricted shipping corridors, an exacting requirement. Should a bridge materialize, it would optimally occupy a narrower locale at approximately 12 miles in length. A drawbridge mechanism proves untenable. 100,000-plus daily vessel passages would necessitate perpetual raising and lowering cycles, generating multi-mile vehicular queues and hour-long delays for drivers stuck in traffic. Length poses no insurmountable barrier. China's Dunyan-Kunshan Grand Bridge extends 104.2 miles, while the Bangmai Expressway reaches 33.5 miles. Height presents the authentic constraint. Contemporary megaships, the evergreen A-class instances, tower beyond 100 feet and require substantial undersea clearance. Future vessel designs will likely exceed present dimensions, obligating engineers to construct clearances exceeding 100 feet. This substantial elevation requirement imposes extraordinary structural demands and construction complexity that makes coordination between bridge operators and maritime interests exceptionally problematic. Yet these challenges pale beside geological realities. Atmospheric disturbances and weather patterns represent manageable concerns. Tectonic activity constitutes the paramount threat, the true reason why a Strait of Gibraltar bridge likely will never exist. Earth's crust comprises shifting plate segments. Boundaries between these sections experience heightened seismic occurrence. Regrettably, the African and Eurasian plates converge precisely beneath this strait. The Azores-Gibraltar Transform Fault bisects the channel, a location where plate movements proceed parallelly, intensifying seismic probability. Consequently, construction in this zone faces systematic exposure to high-magnitude earthquakes. This isn't theoretical. The 1755 Lisbon earthquake, measuring 8.5 to 9.0 on the Richter scale, devastated Iberian and Moroccan territories. The 1960 Agadir earthquake, measuring 5.7 magnitude, wreaked extensive destruction. These weren't anomalies. They represent inevitable consequences of plate tectonics. Alternative water crossing projects seldom encounter this hazard. The strait's specific geography renders it uniquely vulnerable. Any bridge constructed here isn't a question of if an earthquake will occur, but when and how devastating it will be. Supplementary investigations identified additional complications. The seafloor composition contains quaternary clay channels, unstable sediment accumulations susceptible to shifting and failure under pressure or seismic stress. These soft, unconsolidated deposits present formidable anchoring obstacles. Pylon stabilization and structural security become exceptionally uncertain. Geologic consensus warns that catastrophic failure potentials stem inherently from the region's crustal characteristics, rendering any construct fundamentally precarious. Beyond geology lies another immovable obstacle: politics. Project financing constitutes critical consideration. Estimates range from $5 billion to $20 billion, necessitating either bilateral cost-sharing or external backing. Critically, the economic case remains unconvincing. Ferries accommodate approximately 5 million annual passengers annually. Aviation and private maritime options satisfy leisure travel. Freight logistics favor maritime routes. Cargo shipping remains economically efficient given the abbreviated distance. Revenue generation thus appears questionable for either government. More significantly, existing shipping lanes generate substantial returns for both Spain and Morocco. An intercepting structure might redirect these gains adversely. The Öresund Bridge, connecting Denmark and Sweden, costing approximately $4 billion, exemplifies how monumental infrastructure investments frequently underperform financially. Foremost among barriers stands the diplomatic relationship, or rather, the absence thereof, between Spanish and Moroccan administrations. Coordination has proven elusive, with competing national interests overshadowing collaborative potential. The roots run deep historically. Britain's establishment of Gibraltar as a territorial possession originated in 1704, when Anglo-Dutch forces seized it. The 1017 Treaty of Utrecht formally ceded Gibraltar to Britain, where it remains an overseas territory. Gibraltar's contemporary population predominantly rejects reincorporation into Spain, having developed distinct identity under British administration. Spain maintains competing territorial claims, the Moroccan enclaves of Ceuta and Melilla. Following 1912 treaty formalizations, Spain controlled vastly larger Moroccan territories. Morocco achieved complete sovereignty over most territories by 1969, yet Ceuta and Melilla remained Spanish. Contemporary Morocco designates these territories as culturally integral and demands repatriation, a perspective Spain contests. Spain's reluctance stems from strategic commercial position rather than historical legitimacy. This territorial deadlock generates the discord preventing collaborative infrastructure initiatives. Bridge proposals haven't monopolized conception. Tunneling represents a historical alternative. The 1930s witnessed Spain's initial tunnel exploration to facilitate vehicular and rail passage beneath the channel. Seafloor surveys identified extremely hard rock composition exceeding excavation capacity. Tunnel consideration resurged during the 1980s when Spain and Morocco reopened discussions. Technological advancement hadn't sufficiently matured, proposals again stalled due to governmental tensions and technical uncertainties. By 2003, both administrations contemplated undersea rail infrastructure utilizing standard European gauge specifications, though neither nation had converted their existing systems. The 2008 geological survey reconfirmed prior conclusions. The shortest distance routing presented unfavorable construction conditions. Engineers recommended westward deviation toward Tarifa, connecting to Tangier, lengthening the crossing to 14 miles. The completed structure would span 21 miles, integrating with Spain's high-speed rail infrastructure. Planning commenced but stalled due to minimal intergovernmental discussion. April 2021 witnessed renewed commitment when Spanish and Moroccan ministers convened in Casablanca. February 2023 scheduled high-level bilateral discussions. Present timelines: Project 2030 construction commencement, though historical stalling patterns generate skepticism regarding timeline fulfillment. Despite obstacles, engineering imagination hasn't surrendered. Professor T.Y. Lin, recipient of President Reagan's 1986 National Medal of Science, formulated an audacious design connecting Point Olivos and Point Sears, 8.7 miles apart. His revolutionary proposal incorporated 3.1-mile peer-to-peer spans, substantially exceeding all existing structures. Computer modeling identified his hybrid stayed suspension bridge concept as optimal. 1,096 cost estimates reached $15 billion. This vision remained unrealized. Architect Eugene T. Sway proposed an extraordinary alternative: the Strait of Gibraltar floating bridge. Rather than traditional construction, T. Sway envisioned submerged infrastructure, not seafloor resting, but suspended approximately 650 feet deep, permitting vessel passage overhead. An intermediate artificial island would house resort facilities, wind installations, maritime infrastructure, and commercial operations. Combined wind and tidal generation would theoretically produce sufficient renewable electricity powering much of Morocco and southern Spain. The integrated structure would function simultaneously as transport corridor, power installation, and tourism destination. T-SWE allocated 24 vehicle lanes. Floating infrastructure alone projected approximately $10 billion. No current realization efforts exist, yet T-SWE's multifunctional paradigm might inspire future intercontinental development.